Good morning to Professor. Today our group Dinosaur will present the paper is LLM guided deep reinforced learning with constructive safety regularizations for autonomous driving. Our group have me, Darryl Chong, Li Yiqian, Wang Xingyi, Zhang Tianying, Chua Li Rai, and Woon Kai Fan. So this paper is related to deep reinforced learning, large language model, and autonomous driving decisions. So the paper proposed a framework called LSA-DQN, which stands for LLM Guided Safety Aware DQN. The objective is to improve safety in highway driving decisions, reduce collision risks, and still maintaining driving efficiency. Deep reinforced learning or DRL is a method where an agent learns by interacting with an environment. The environment gives the agent a state and a reward or penalty. Based on this, the agent chooses an actions and improve its policy over time. In this paper, the agent is the autonomous vehicle and the environment is highway traffic. So driving is safety critical because vehicle move at high speed, multiple lanes require frequent decisions, and surrounding vehicle may behave unpredictable. If the vehicle makes a wrong decisions, it may cause a serious collisions. Next, my member will explain the specific challenge addressed in this paper.
One of the biggest challenges in autonomous driving is making safe and efficient decisions in dynamic highway environments. High-speed traffic and unpredictable vehicle behaviors make real-time decision making very difficult. Although the RL has shown strong potential, it still has several limitations. First, traditional DRL models use fully connected networks, which flatten traffic information and weaken vehicle interaction modeling. Second, methods like DQN may overestimate Q values for unseen actions, leading to unsafe decision. Third, many existing methods rely only on collision penalties, which cannot provide clear safety boundaries during exploration. Therefore, this paper proposes LSADQN, a safer and smarter decision-making framework. It combines multi-head attention, LLM-guided safety reasoning, and hybrid safety regularization to improve both driving safety and traffic efficiency.
My name is Woon Kai Fan. I will introduce the methodology. For this part, I will explain the DRL model architecture used in the study. The proposed model is called Multi-Head Attention-Based Double DQN or MHADDQN. The announcement driving task is formulated as a reinforcement learning problem, where the agent observes the traffic environment, choose an action, receive a reward, and learn from the result. The input of the model include information from the ego vehicle and surrounding vehicle, such as their position, speed, and movement. Based on this information, the agent select one of five driving actions: lane left, idle, lane right, faster or slower. The study used double DQN instead of basic DQN because basic DQN may overestimate Q value. So this can make the agent choose risky actions. Double DQN helps to reduce this problem and make the learning process become more stable. For the network architecture, there are four main layers. First is the embedding layers, transform raw vehicle features into useful features vectors. Second is multi-head attention layers, helps the model focus on important surrounding vehicle. This is useful because not every vehicle has the same impact on the ego vehicle decision. Third is the add and norm layers. It helps to keep important information and stabilize training. Finalize, the MLP layers produce Q value for each position action. The agent then choose the action with the highest Q value. Overall, this architecture helps the agent better understand complex highway traffic and make safer and more efficient driving decisions.
This framework introduces an LLM guided safety classification mechanism for the system. First, the system uses physics-based rules such as vehicle distance and time to collision, or TTC, to quickly evaluate driving risk. Clearly safe experiences are stored in the safe replay buffer, while dangerous experiences are stored in the unsafe buffer. For ambiguous situations, the framework uses GPT-4 to perform safety reasoning based on the driving context and surrounding vehicle information. The final output is a safety label, either safe or dangerous, which helps improve later reinforcement learning training. After classifying experiences into safe and unsafe categories, the framework applies hybrid safety regularization. First, conservative cue learning, or CQL, encourages the agent to prefer safe actions and avoid non-risky behaviors. Second, margin-based contrastive penalization, or MCP, explicitly lowers the Q values of unsafe actions. By combining these two methods, the framework learns safer and more robust driving policies in complex environments. Finally, the framework combines the original DDQN laws with both CQL and MCP regularization terms into a unified training objective. This allows the agent not only to learn driving strategies efficiently, but also to improve safety and reduce risky behavior during decision making.
And one thing I will introduce the dataset and the experimental outcomes of this paper. For the experimental setup, this paper does not use a real-world driving dataset. All data are generated with the highway event simulator. The authors built a dense fallen one-way highway scenario, and the surrounding vehicles' longitudinal movement follows IDM, and their lane-changing behavior follows MOBRL. For the state representation, the agents observed the ideal vehicle and its nearby vehicles, including their relative positions and relative velocities. The action space contains five discrete actions: lane left, idle, lane right, faster, and slower. Finally, all models are trained for 5,000 episodes and tested over 1,000 independent episodes. The main metrics are reward, speed, episode length, and collision rate. Next, let's look at the experimental outcomes. From the ablation results, the baseline DDQN has a collision rate of 17%. After adding the multiple head attention network, ADQN reduced the collision rate to 4.5%. While keeping the highest average speed 29.29 meters per second. Then, after adding CQL, ACDQN further reduced the collision rate to 3.3. Finally, the full LSADQN achieves the lowest collision rate, only 0.9. So we can see that each added module improves safety step by step. However, there is also a safety efficiency trade-off. The safest model has a slightly lower average speed, decreasing from 29.29 to 27.91.
My name is Leroy, and I'll be presenting the conclusion for our assignment. In conclusion, the LSA DQN framework successfully improved both safety and efficiency in autonomous driving. The model reduced the collision rate from 17% to 0.9% while still maintaining stable driving performance. Multi-hit attention helped the system better understand surrounding vehicles, while LLM guidance improved safe decision making in complex highway environments. In our opinion, this research is significant because it shows how large language models can enhance safe reinforcement learning, allowing the system to learn safer behaviors proactively instead of only learning from collisions after they occur. We also found the integration of GPT-4 with DRL highly innovative, as it demonstrates the future potential of combining language intelligence with autonomous systems and robotics. Although there are still limitations such as the LLM latency and the need for real world testing, this study provides a strong foundation for safer and more reliable autonomous driving technologies in the future. And that is all. Thank you for listening.